Good afternoon. My name is Tunde Hui. So this afternoon I want to talk about simple harmonic motion. So to talk about simple harmonic motion, there are times we have to really talk about how do we describe a simple harmonic motion. So we have to talk about the amplitude of the wave. We talk about the period and the frequency. But to start with, what is a simple harmonic motion? A simple harmonic motion is simply a wave, the movement of a material about a main position. Just like we have on this graph, on this paper. This is a simple pattern of a simple harmonic motion. Now the amplitude of the simple harmonic motion is the maximum displacement from that main position. When we talk about the main position, this is what we refer to as the main position, the zero level positioning. So the amplitude is the maximum displacement from this main position to that particular amplitude position. Then the period of a simple harmonic motion is the time taken for one complete oscillating body, a complete oscillation. That's the period of the simple harmonic motion. Then also for the frequency of the simple harmonic motion is actually the numbers of oscillation made in 1 second, numbers of oscillation per second. That's it, how frequent the oscillation was. So then for a simple harmonic motion, we can also talk about it as being a form of oscillation. So for oscillation, we can have two types of oscillation. We can have a natural oscillation, we can have a forced oscillation. So which one is a natural oscillation? When a body goes about simple harmonic movement naturally without somebody disturbing it. Then for a forced one, a forced oscillation is actually the one that is caused by somebody, an object, or any natural being. So that's forced oscillation. Actually, both of them are forced oscillation, but one is actually free, then the other one is instigated. So what are examples of simple harmonic motion? For example, when we have a guitar and we pluck the string of our guitar and it starts moving up and down, that is an example of a simple harmonic motion, when the guitar string moves up and down about a main position, such that it forms a wave pattern of this. So that's an example of simple harmonic motion. Also for electromagnetic wave, it's an example of a simple harmonic motion where we have the electric and the magnetic aspect of the wave moving at right angle to each other. And we another example of a simple harmonic motion is the vibration of the atom of molecules about a main position. That's another example of simple harmonic motion. So let's talk about we've talked about some parameters. We've described the simple harmonic motion using some parameters, that is the amplitude, the period, and the frequency. So also let's talk about the velocity of a simple harmonic motion. So what is the velocity of a simple harmonic motion? The velocity of a simple harmonic motion is actually given as the change along the change of displacement per the time. In the same way, the acceleration of a simple harmonic motion is given as the change in velocity all over time. Now, another parameter we also use to describe the simple harmonic motion is the concept of frequency and angular frequency. Don't forget, the frequency of a wave of an oscillating body is given as 1 all over time period. That's the frequency of oscillation for a particular body. So the angular frequency for a simple harmonic motion is given as 2 pi the period. That is, we talk about simple harmonic motion in terms of the phase in the radian, when the angles are measured in radian. So if the angular velocity is given as this, 2 pi f, interchanging the formula, the angular velocity is still 2 pi all over time period, where the period also is also equivalent to 2 pi all over angular velocity. So this is a graph of the motion of the simple harmonic motion in phase. This is the maximum displacement, which we referred to earlier as the amplitude. At this point is what we have pi all over 2, which is the 90-degree angle in radian, when our angles are measured in radian. Then again, we want to talk about the relationship between the displacement of a simple harmonic motion with the time. So the equation is given as x is equal to x naught sine wt, where x is the displacement at a particular time. The x naught is the maximum displacement along the curve, sine the angular frequency, which is given as 2 pi f. So also the wave of a simple harmonic motion can be represented in terms of the cosine function. So what's the difference between the sine function and cosine function? For the sine function of representation of the simple harmonic motion, the wave starts from the 0 mark. So that is why we use x is equal to x naught sine wt. But if the wave doesn't start from the origin, then we can represent the wave function as x is equal to x naught cos wt. So that's the difference about this. So then we want to talk about damping of oscillation. So how do we damp oscillation? Oscillation can be damped naturally or forcefully. The same way oscillation can be set up naturally or forcefully. So how do we damp oscillation forcefully? By the use of shock absorber. These shock absorbers actually are damped. They actually absorb the energy of the oscillating body. By so doing, this body loses its energy and doesn't oscillate again, doesn't vibrate again. So for a naturally oscillating body, the oscillation can be damped by friction or by air resistance. So from the graph, as you can see, you have the graph of the oscillating body. Can you see? It goes till it goes to 0 level. No more energy. So what are the usefulness of damping of oscillation? It's applicable in the construction of our motor cars, our vehicles, where you have shock absorber being installed in motor vehicles, in motor cars. For example, when we are going on the road and we hit a bumpy road, this shock absorber prevents the vibration up and down movement of the vehicle by absorbing the energy. By so doing, it gives us stability. Also, in the same way, bridges are constructed with installed damper, such that when vehicles are moving on the bridges, and the energy of this vehicle can be absorbed, so that the bridge will not be going up and down. So this absorber actually they damped the energy of movement of this oscillating or vibrating body. So also we want to talk about resonance. So what is the resonance? Resonance is actually a phenomenon